Okay, in this segment we're going to be looking at the parallel operator. And just going over some of its properties. And we'll be talking about something like a resistive voltage divider and a resistive current divider if we have time. So the parallel operator will be defined by x parallel y is basically 1 over x plus 1 over y to the minus 1, or as we said last time, if we multiply top and bottom by xy, we would get xy over x plus y. And so it's pretty obvious from just the symmetric nature of this expression that that the parallel operator is commutative. Which means that x parallel y is equal to y parallel x. It's associative, which means that if we had x parallel y, and then that paralleled with z, that would be equal to x parallel y parallel z. And because that's true, we can unambiguously drop the parentheses and just say that's x parallel y parallel z. All of these properties basically follow from the definition and the associativity, commutativity, and whatnot of multiplication and addition. So we're not going to go through and prove them all, but we're just going to state the properties. So just like there's a unit element for addition, that would be 0, and for multiplication that would be 1, the unit element for the parallel operator is basically infinity. So x parallel infinity is equal to x. You can think of summation as the sort of series operator, and the short circuit is the unit element for the series operator. Well, likewise, the open circuit, or the infinite resistance, would be the unit element for the parallel operator. If I put an open circuit in parallel with a resistance, I just get the resistance as the equivalent, right? Just like if I put a short circuit in series with a resistor, I just get the resistor itself. Okay, so you can multiplication distributes over the parallel operator just like it does over addition. So it's distributive. So we have some constant times x parallel y. That will be equal to cx parallel cy. And we'll be using this in some cases to push a constant through a parallel combination, or to factor a common factor out of a parallel combination. We need to define an order of operation. And this is going to be just our convention here, but basically we're going to say that parallel comes between multiplication and division and addition and subtraction. So for instance, if I have x plus y parallel z, we will interpret that as being x plus y parallel z in parentheses, so that the parallel combination happens first and then the addition, whereas if we had something like xy parallel z, we would interpret this as xy being done first parallel z. Okay? So with that in mind, we want to talk about a couple more things. So if x and y are both positive, which is going to be the common case that we're dealing with when x and y are resistances, then x parallel y is less than x, and x parallel y is less than y. So the parallel combination of two things is less than both of the things that we're combining. And if x is much less than y, then x parallel y is approximately just x. So just like if we have a series combination of two resistors that have a very large disparity in their values, we say that the larger resistor dominates the series combination because the much smaller value is negligible in the sum. In the case of a parallel operator, the thing that is much smaller dominates the parallel combination. Okay, the limiting case for that would be the short circuit and the open circuit, the unit elements. X parallel x is just x squared over 2x, which is just x over 2. Right, so it's just half of the values if you take the same thing and parallel it with itself. If we have x parallel the same thing, parallel x n times, this is just x over n. So if I have 10 1K resistors in parallel, then that's equivalent to a 100 ohm resistor. That's basically what we're saying there. Okay, so these are some basic properties and some useful things about the parallel operator. And like I said, we'll be using that as a convenient notation all semester long. Okay, so I'm going to talk about a resistive voltage divider. Now you've all seen this probably in ISIM and maybe in a physics class, but basically we have here two resistors in series. We've got some input voltage, and we're interested in what is the voltage that appears here across R2. That's our output voltage. Okay, so this is a very commonly occurring scenario, subcircuit, and we're going to analyze this, and the result of the analysis will be such a useful thing that we would want to kind of remember it, if ideally, so that we can bust it out without having to solve this problem again and again and again. So here, our strategy is going to be to say, well, if we knew what In is, that current flows through R1 and then through R2, we could calculate V out as that current In times R2. Right, so V out is equal to In times R2. But In we can calculate by just recognizing that these two resistors in series behave as an equivalent resistor of R1 plus R2, and so we can just get In as Vn over R1 plus R2. So this is equal to Vn over R1 plus R2 times R2. And so usually what we do is we rearrange this a little bit. We put the R2 over here and we put the Vn over here. and we wind up with R2 over R1 plus R2 times V in. So V out. And this thing is called the voltage divider ratio. So I imagine you may even remember this from ISIN. It's a useful thing. I would put it in your L1 cache. And if we were to plot what's called a voltage transfer characteristic of this relationship, which is a plot of V out versus V in, and this is just a static plot of the output voltage versus the input voltage, what we'd find is a straight line. And the slope of the line here is just the voltage divider ratio. Now this generalizes quite nicely to the case of, say, n resistors connected in series. We could say something like R1, Ri, Rn. If we're interested in the voltage across the ith resistor, V sub I, we can take the same sort of approach and say that, well, the same current is going to flow through all these resistors because they're all connected in series. So Vi is equal to In times Ri, and we can get In as Vn divided by the equivalent resistance of these n resistors in series, which is just R1 plus R2 plus ... up to Rn. So that's equal to Vn So that's sort of the n-way generalization of our two-way voltage divider. The two-way one is probably the most useful thing to remember. Okay, sort of the dual situation of this would be something that's probably a little bit less familiar, and that's called the resistive current divider. Okay, this is, like I said, probably less familiar to you, but it turns out that for a lot of the circuits that we'll be looking at, especially later on in the class with respect to, or that are made from transistors, it turns out that the current divider is actually probably even more useful than the voltage divider is. And so in the current divider, we have basically an input current source, and we have two resistors connected here in parallel. And this total input current is going to divide into two pieces. And we're interested in, say, I out is the current flowing through this resistor R2. Okay, there's going to be some voltage here, V in, that develops. And if we knew what V in was, so V in is the voltage across both R1 and R2 because they're connected in parallel. So if we knew what v in was, we could write I out as v in over R2. But we can easily find v in by recognizing that we can collapse R1 and R2 into a parallel equivalent of R1 parallel R2, and by Ohm's law, v in is going to be I in times R1 parallel R2. So we can write this down as R1 parallel R2 times I in divided by R2. And so we can group the resistors together and write this as R1 parallel R2 over R2 times I in. So this is the current divider. And this thing here is called the current divider ratio. And if we wanted to, we could plot a current transfer characteristic, which is just like the voltage transfer characteristic. It's a plot of I out versus I in. And it would again just be a straight line. And the slope of the line is the current divider ratio. So the slope is R1 parallel R2 over R2. It's not very clear. R1 parallel R2 over R2. There are a couple of different ways that we can express this. We can take that R1 parallel R2 over R2. We can expand out this parallel combination as the product over the sum, and that would become 1 over R2 from the 1 over R2 here times R1 R2 over R1 plus R2, and so the R2's cancel, and that is just R1 over R1 plus R2. And a lot of developments of the current divider ratio will have it expressed in this form, which is fine. It only applies to a two-way current divider without some gyrations or gymnastics. But the way that people will say it in words is that we've got these two branches here, and the current flowing through the branch that we care about is equal to the input current times the resistance of the branch we don't care about, divided by the sum of all the branch resistances, the two branch resistances. Whereas the way that we developed it here, we get the parallel combination of the two branch resistances divided by the branch resistance of the current we care about. And it turns out that this form generalizes quite nicely to the n-way case, as we'll see. But people tend to like this form for some reason, because I guess it looks a little bit like the voltage divider, and so that, I guess, makes it more familiar or something. Anyway, there's another form, and if we were to express this in terms of conductances, we would get basically R1 parallel R2 divided by R2. Well, this is equal to 1 over G1 parallel 1 over G2 divided by 1 over G2, and the G2 of course will pop upstairs, so that's G2 times 1 over G1 plus 1 over G2. Now the 1 over G1 and the 1 over 1 over G2 just become G1 plus G2. So this is equal to G2 over G1 plus G2. So expressed in terms of conductances, we get something that is actually also quite like the current divider or the voltage divider ratio, only it's the conductances instead of the resistances. So it's the conductance of the branch whose current we care about divided by the sum of the branch conductances. And it turns out that just like the parallel form, the conductance form also generalizes quite nicely to the n-way current divider. So think about the n-way current divider. Where we basically have some total current let me put them over here. We want to have a current flowing through the ith resistor. Well, again, Vn appears across every single resistor. It's the voltage across every resistor, so I sub I is just V sub I, or rather Vn, over R sub I. And the parallel combination of these resistors gives us the equivalent resistance of the whole thing, so we can get Vn as basically R1 parallel parallel Rn divided by Ri times In. And we can apply that same idea that we had with a two-way conductance divider. It generalizes quite easily so that we would get Gi divided by G1 plus plus G sub n times In. So in the case of the resistance of the branch whose current we don't care about divided by the sum of the branch resistances form, we can apply that rule or that current divider form in this case, but what we have to do in order to apply it is to take all of the other resistors that we don't care about, so it would be R1 up to Ri minus 1 and Ri plus 1 up to Rn, and lump them together into a single equivalent resistor. And then we have a two-way current divider, and then we wind up with a simple two-way current divider with equivalent resistances. And so what that would look like, and I don't even have good notation for it, would be something like I sub I equals parallel combination J not equal to I of Rj. So this is the parallel combination of all the resistors that are not Ri divided by parallel combination J not equal to I of Rj plus Ri times I in. So this is doable. It's a little awkward, and because the emphasis is kind of on the resistance of the branch, or the equivalent resistance of the branch that we don't want to know the current through, it seems kind of like not the best choice. So my recommendation would be this one or this one, depending on whether it's more convenient to work with resistances or conductances if you're dealing with an n-way current divider. Okay, I think that's going to be it for this segment, and we'll see you next time.